Hello, pre-calculus friends. This is a video on lesson 2.6, which is about rational functions and their graphs. And first off, we need to define a rational function. That's how we need to start, of course. And so basically, they're quotients of polynomial functions. This means that rational functions can be expressed in this way. Really, the main thing to think about there is that rational functions are functions where you see variables in the denominator. If you don't have variables in the denominator, then it's not a rational function. So that's really what determines that we have a rational function. Okay, so remember rational means fraction, ratio is fraction. So that's basically, we're talking about a function that is a fraction where there are x's in the denominator. So here we have an example. Now, one of the things we talk about with rational functions is their domain. This is one where it matters. This is a function where the domain is not unlimited. It is limited. There are restrictions to the domain. And that is, since we have a denominator, we have to make sure the denominator is never 0. Okay, since there are x's in your denominator, there could be values of x that would make that 0. So what we're going to look at here is what would make the denominator 0. Generally, a first step that is helpful in trying to figure that out is factoring the denominator. If the denominator can be factored, you factor it. So like here, they factored it and they said, okay, I've got 3 factors, x, x minus 2, and x plus 5. X equals 0. Well, if x is 0, that's a problem. Set x minus 2 equal to 0, and we find out that if x is 2, that's a problem. Set x plus 5 equal to 0 and solve, and you find out that if x is negative 5, that's a problem. So x is or the domain is the set of all real numbers except 0, 2, and negative 5. That's expressed lots of different ways in different classes and different contexts. And we're going to talk about how it's expressed in Math Lab, how we need to express it in Math Lab. Sometimes people will just put x can't be equal to 0, 2, or negative 5. Sometimes we do it in interval notation, where we say, well, x can be everything from negative infinity up to negative 5, and then from negative 5 to 0, and then from 0 to 2, and then from 2 to infinity. That's one way to do it. And notice that these are parentheses, which means it does not include that number on that side of the interval. So negative 5 is not included here. 0 is not included here. 2 is not included there. So there are different ways to say that, but basically at this point we're just saying all real numbers except and saying what can't be. So here it's already in factored form. So this would be x equals 0, so x can't be 0. Basically we could just write it that way if we want to. And here we don't want x minus 3 to be equal to 0 either. So that means x can't be 3. So all real numbers, this is my domain, all real numbers except 0 and 3. However you express it, you just have to make sure you make the point that it cannot be those answers. Sometimes people will accidentally say, oh, the domain is 0 and 3. If you say it that way, you're telling me that the only x's that would work are 0 and 3, which is completely the opposite of what's true. Okay, so be careful about how you express that just to make it clear that these are the exceptions. These are what we call the domain restrictions. Now over here, this cannot be factored any further, so we just have to say, okay, we've only got one factor in our denominator, and we have to make sure that's not going to be equal to 0. So let's see what we're doing here. Now, notice a second ago I said all real numbers except, so we're dealing with real numbers here. So if the only thing that would make this 0 is if I had imaginary numbers, those aren't real numbers. So I don't have to worry about it. This means there are no domain restrictions because all real numbers are fine. The only problem would be imaginary numbers. So all real numbers is my answer, and that's the expression, or that's the symbol, excuse me, for all real numbers. Okay, so let me just take a second to show you how this is dealt with in the Math Labs under Blackboard context. They go ahead and say, select the correct choice below, and if necessary, fill in the answer box to complete your choice. So either we're saying there are no restrictions on the domain of the function up there, r of x, which would mean all real numbers, or we're going to say the domain has to be all real numbers except. This is set notation. It's saying the set of all values of x, given that x cannot be equal to, and we're going to tell that it can't be equal to -10. So that's what you're doing, is you're putting in those domain restrictions into the set notation, but they've got the set notation already set up for you. Okay, moving on to our next objective here in this lesson is to look at vertical asymptotes. It says the line x equals a. In other words, x equals a number. Vertical lines are always x equals a number. X equals 3, x equals -5. Those are vertical lines. So the line x equals a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as x approaches that number. In other words, basically, if it keeps going up and up and up and up and up and never and closer and closer and closer and closer to that, but never crosses over, or down, 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 etc. Okay, so a couple of different ways that they're basically just giving us examples here of how we can express this. But the thing I want to point out to you here. Actually, no, that's on the next slide. So let's just go ahead and talk about this. The way you probably did this in pre-calc, and let's just take a second and analyze it this way. When we were looking for asymptotes, basically really characteristics of the graph for rational functions that you did either in pre-calc or algebra 2 in high school, is you started by factoring everything. So I would suggest you want to factor the numerator and or denominator, depending on what you're looking for. Denominator. But if you're looking for everything, if you're trying to figure out everything about your functions graph, do both. Now, factors in the denominator that have a match in the numerator. If you have the same factor in the denominator and the numerator, that factor corresponds to a hole in the graph. If you have a factor in the denominator that does not have a match, so factors in the denominator that, or you could say just in the denominator only, I'm going to say that don't match any factors in the numerator, those indicate a vertical asymptote, which is what we usually say VA for vertical asymptote. Now let me point out what I'm saying. Another way of saying this, factors in the denominator that have a match in the numerator, that means factors that would cancel. Like you get it factored and it's something like this. And you say, oh, I've got x minus 2 on both top and bottom. That indicates that there is a hole at x equals +2. In other words, the x value that goes with that factor, which is always the opposite sign, the x value that would make this equal to 0. All right, in that same example, we'll say this would be a hole at x equals 2 for that example. Same example, we would have a vertical asymptote at x equals -3, because that's a factor that is in my denominator that I don't have a match for in the numerator. Okay? So locating vertical asymptotes, that's basically what I just went over. So I'm looking here, and I have two factors in my denominator. Neither one of them has a match in the numerator, so both of those are going to indicate vertical asymptotes. So my vertical asymptotes are at x equals 0 and at x equals +3. Now over here, it's basically whatever, this is only one factor for the denominator, so it's whatever would make this 0, but we've already talked about the fact that the only thing that's going to make that 0 is a non-real number, is an imaginary number. So we're only talking about real. Anytime you're going to graph something, we only graph real numbers. You can't see imaginary numbers on a graph. unless you're talking about the complex plane, but we're talking about graphing a rational function. So we're not talking about just imaginary numbers. We're talking about graphs of everything. So on the coordinate plane, the standard graph that we use, you're not going to see any imaginary numbers. So I would just say this has no vertical asymptotes. Now our next goal here has to do with something that's kind of like end behavior. Now, you notice it says describe. You notice it says, sorry, I'm stumbling over my words, describe the behavior, but not necessarily the end behavior, because we have things happening in the middle of the graph that we have to describe. It's not just what happens on the ends. So the first thing you need to know here, and it's kind of hard to see on this has as x approaches 1, and then there's a little plus sign. And this says as x approaches 1, and then there's a little negative sign. Same thing here. It says as x approaches -2 with a plus sign, -2 with a little negative sign. So let's talk about that. If I say as x is approaching 1 and I have a little plus sign, then what I'm saying is as x approaches 1 from the right, from the positive area, from the higher values coming in toward the 1. If I say this, notice it's behind the number. This is not saying -1. This is 1 and then a little negative, right where you would normally see an exponent. This is saying as x approaches 1 from the left. In other words, from negative land, which is on the left. Okay, so looking at this particular example, and I'm going to see if I can manually zoom in, i.e. adjust my dock cam without making you ill. Hopefully that worked. And I'm going to see if I can focus this a little bit better, so hang on one second. Okay, there we go. It says as x approaches 1, and then the plus sign. X equals 1 is right here. So we're saying what's happening to the y values, that's what we're saying for f of x, what's happening to the y values as we come toward that from the right. So if we're coming toward that vertical line from the right, my y values are going up, 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 up. So that is f of x is approaching positive infinity. If we're coming toward that from the left, and we don't need to worry about way over here, but immediately from the left. As I get closer and closer to that from the left, my y values, my f of x, which is y values, is going down, 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 down. So it's approaching negative infinity. All right, same thing happens here. As x approaches -2 from the right, here's that vertical line at -2. So from the right, as we're getting close to it, we're going down. So that's negative infinity. All right, f of x, as x approaches -2, with a minus behind it, which means from the left, my function values are going up. So I say f of x is going toward positive infinity. And then finally, this is really the ends. That would be kind of end behavior. So as x is approaching infinity from the right, even though this kind of looks like it crosses it, we're going to say this is going toward 1. And as x approaches negative infinity, this is going toward 1. And you know, that actually, I don't know, if we had that equation, I might investigate it further, because it might actually be approaching 0 over here. It kind of looks like it goes down across that. Okay, but it doesn't really get close to 0 at all, so I'm going to stick with the 1 for here, for this particular example, with an absence of any further info. Okay, so now we've talked about vertical asymptotes, we've talked about holes, it's time to talk about horizontal asymptotes. All right, horizontal asymptotes are things that basically our graph approaches, gets closer and closer and closer and closer to. We usually say, but does not cross. Sometimes they can cross the asymptotes. Sometimes one part of a graph does and one part doesn't, so it can be an asymptote just for part of the graph. But basically, anytime it has this behavior where it seems to be getting infinitely closer all the time as we go in a certain direction, that's an asymptote. So these are horizontal asymptotes. And remember, horizontal lines are always y equals some number. So that's how my horizontal asymptotes will be as well. So here is the rule written out. You know, college textbooks aren't always known for being the easiest thing to read, so I'm going to just summarize this a little bit better. Okay, so we need to look at the degree of the numerator and the denominator. In other words, here, that's what they're talking about with n and m, the degree, the biggest exponent. If the degree of my numerator is less than the degree of the denominator, then the horizontal asymptote is just y equals 0. If the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. You might remember from doing this earlier that that's when we would look for a slant asymptote. But just in terms of horizontal asymptote, there's not one. If they have the same degree, then our horizontal asymptote, and if you're wondering if I'm laughing here, these are HA is for horizontal asymptote. It's y equals whatever the leading coefficient of the numerator is over the leading coefficient of the denominator. In other words, here it would be the a over the b. Leading coefficient of the numerator over leading coefficient of the denominator. All right, so let's look at a few examples there. Here, the degree matches. The top is squared, the bottom is squared. They both have a degree of 2. That's when this third case is coming into play. I take y equals, and then I take the leading coefficient of the numerator and the leading coefficient of the denominator and make a fraction out of them. It's almost like we just ignore everything after the very first thing we see on both numerator and denominator. So that would be y equals 15 over 3, which I'm going to simplify, or y equals 5. Next up, we have 15x over 3x squared plus 1. Here, the degree of the numerator is 1. The degree of the denominator is 2. So the degree of the numerator is smaller than the degree of the denominator. That's this one right here. My horizontal asymptote is y equals 0. And finally, here we have a degree of 3 in the numerator and a degree of 2 in the denominator. So the degree of the numerator is greater than, degree of the denominator. And so there is not a horizontal asymptote. So I'm just going to say no horizontal asymptote. Okay, the next graph characteristic we're looking at here is just a quick recap of the concepts of odd graphs and even graphs. All right, or odd functions and even functions, graphs of odd functions and even functions. This one is odd, this one is even. All right, now it doesn't just correspond to, oh, my degree is 2, 2 is an even number, or oh, my degree is 3, 3 is an odd number. Although we like to try to boil it down to that. That's not all there is to it. Here's the rule for how we could actually find out if we have the equation. What this is saying is, if I plug in negative x in place of x, and the thing that I get once I've simplified everything is exactly the opposite. In other words, it's the same as if I took negative 1 times the original function. All the signs are the opposite. Then that's an odd function. And what an odd function has graphically is called origin symmetry. Origin symmetry is another way of saying what we generally call in geometry rotational symmetry. So this is rotational symmetry, specific type, rotational symmetry of 180 about the origin. 180 degree rotation about the origin. That's what we mean by origin symmetry. Okay, is that if I turned it 180 degrees around the origin, it would look the same. So you can see that this one is like that. If I turned it exactly upside down, it would look the same. Notice that this is one of the parent functions we use a lot with rational functions, is 1 over x, and so there's that parent function graphed for us. Here's another parent function we use a lot, 1 over x squared. This one is an even function. All right, even functions are symmetrical across the y-axis. So they're just regular line symmetry, and the line of reflection is the y-axis. All right. The way to tell algebraically, looking at the equation, if you have an even function, is when you plug in negative x in place of all the x's, you get the exact same thing once you've simplified as you started with. It looks exactly like the original. Okay? So we're going to come back to that in a little bit, but those are just sort of overviews of what that means and reminders of graphically what it looks like. Okay, I mentioned on that last part that this guy, the one that had the even, was an even function, or the reflectional symmetry across the y-axis, is a common parent function for us to use. And that's what we're doing here. They're saying, let's use this parent function to see what this graph would look like. Well, we've got two things that are different here. We've got this -2, and it's inside the squaring that is happening to x. So we would think of that as being inside what's happening to x, so that would be horizontal. And then we've got this +1, which is not inside the squaring that's happening to x, it's outside. And remember, things that happen outside the main idea of your function are vertical. So this is a horizontal shift. Where is it? 2 to the right. Remember that horizontal stuff, it's always the opposite from the direction when you would think it would be. You would think minus would be to the left. It's actually going to be to the right. All right, so they're shifting, and we're starting with these 2 points and saying these are two easy to see, easy to establish points, and we're shifting 2 to the right. This one's going to move to 1, 1. And this one's going to move to 3, 1 because I changed the x value by adding 2 to each one. Add 2 to each x coordinate. Notice that didn't do anything to my horizontal asymptote. But this part right here, the +1, that's a vertical shift. If you have a vertical shift, that's going to move your horizontal asymptote. So notice that we now have a dotted line here. That dotted line used to be right on top of the x-axis. That's where my natural horizontal asymptote is. We've moved the horizontal asymptote, shifted it up 1, because that +1 is saying vertical shift of up 1. The other thing I moved up 1 was these coordinates. If I add 1 to each y value, then I get my new point. Okay, so +1 here to the y value only gives me a 1, 2. +1 to this 1 here gives me 3, 2. And that's just a good example of a transformation using that particular parent function. You're going to be asked to do that on several graphs on your homework. So let's try a couple. Now let me point out that on many of the ones you graph, they are giving you multiple choice graphs, which is nice because you don't have to supply what the shape looks like in general. They've got the shape for you, you just have to figure out where it is. But if I were trying to figure out the shape here, I would say, okay, my parent function, and I'm just being random and using g, is this. And remember, we have that graphed earlier in our notes here, or actually just on the previous page, it's right there. Okay, so let's go ahead and borrow from that. I'm going to go ahead and take those points. We know that it passes through -1, 1, and it passes through 1, 1. So I'm going to take those. -1, 1, it passes through 1, 1, and it has a horizontal asymptote on the x-axis, which is at y = 0. That's where the parent function is. This is telling me there's nothing happening inside with x there. Nothing else is being squared. X is still by itself. So no horizontal shifts at all. This is a vertical shift down 3. Vertical happens to y. So that means I'm going to go down 3 with each y. That means subtract 3. So my new point is going to be -1, -2 for that point. And for this one, it's going to be 1, -2. And the asymptote is going to change because I'm shifting down. So instead of having my horizontal asymptote at y = 0, it's going to be at y = -3. All right, so that's what I would be looking for in my graph, is those points and that horizontal asymptote. Next one, my parent function here, 1/x. All right, let's see, where's that one? Nope. There we go. That's the one that looks like this. So it goes through 1, 1, and it goes through -1, -1. So let's use those points. All right, 1, 1, -1, -1. And notice here that I actually have, on this parent function, I have 2 asymptotes. I have a horizontal asymptote at y = 0, and I have a vertical asymptote at x equals 0. Just made those a little bit easier to see. Okay, so those are the things I'm going to be shifting here. I've got a horizontal asymptote at y equals 0, and I got a vertical asymptote at x equals 0. All right. What's happening here? The only difference between this and this is the -2. All right. What's happening to x here is it's in the denominator. The -2 is in the denominator. So that means it's also happening sort of inside what's happening to x. So we think of that as inside, and therefore it's horizontal. So this is a horizontal shift right. Remember, horizontal is always the opposite of what you'd think, 2. All right, so that means I add 2 to my x values. So I'm going to add 2 here, add 2 here. That would give me 3, 1, and this would give me 1, 1. So I've shifted things 2 to the right. It's not going to move a horizontal asymptote. If you're going left and right, this line stays the same whether I go to the left or the right, whether I push it to the left or the right. It will move, so that stays the same. It will move a vertical asymptote. We're going to move x values right 2, so that means x equals 0 will become x equals 2. This was not an x value, so we didn't change it. All right, if we're doing a horizontal shift, the x values change. If we're doing a vertical shift, only the y values change. We could have one where we do both, in which case both would change. Okay, the last few questions on your homework are going to ask you to go ahead and take all the knowledge you have about this rational function and use it to do the graph and to figure out everything you need to about the graph. Now, the thing they'll mention in this, in asking you to do this, is they'll ask you to use the 7-step strategy. Okay, so the first time I saw this, I was like, what on earth are you talking about? I know how to find all those things that I need to find on this graph, but what do you mean by 7-step strategy? So let me just walk you through what they mean, because it is all things you already know that we've talked about today, or maybe you already knew before that. Okay, so the first one is determine any symmetry, meaning odd, even. Okay, one thing to remember is functions don't have to be one or the other. Unlike numbers, it's not like, everything is either odd or even. Many, many, many functions, infinitely many in fact, are neither. Okay, so that's a distinct possibility. Now, how can I find the symmetry? Well, there's a few things. Let's suppose that I recognize the function as one of these guys. All right, well, if I take this guy, it is even right now. If I do a vertical shift, it's still going to be even. If I see a horizontal shift, it's not going to be even anymore, because now it's moved off the y-axis. It's moved to the right or to the left of it. Okay, this one, it's got origin symmetry right now, but pretty much any shift is probably going to throw that out. All right, a reflection might not, but we haven't been dealing with reflections. So you can kind of think about some of those things, but also remember I told you that if you plug in -x, an odd function, once you simplify it, will give you the same as if you just took your original function and multiplied by -1. An even function, excuse the bell, it'll look exactly the same once you simplify everything. So that's one way to figure it out algebraically. Technically, you're not supposed to be using a graphing calculator in this class, but of course, if you could graph it, that'd be easy to see. However, you can use scientific calculators that have a table of values, and you could always look at the table of values and see if it, seems like something that would be symmetrical. That might help you as well. Okay, and your homework's going to walk you through these, so I'm not going to belabor the point too much. But next, you're going to find the y-intercepts, if there are any. Remember that to find a y-intercept, you can plug in x equals 0. That's how you find your y-intercepts. You find out where x is equal to 0, because x is equal to 0 on the y-axis. Next, you find your x-intercepts. Well, that means where y equals to 0. Now, that's the same thing as saying f of x equals 0. Now, usually what that means in this case is that means set your whole function equal to 0. So let me remind you, if you have a function that is a rational function, like let's say I have this. If it's rational, when is a fraction equal to 0? A fraction is equal to 0 when its numerator is equal to 0. It's undefined if the denominator is equal to 0. So we don't care about the denominator at all here. We would say, when is this numerator 0? What makes it 0? And we would say, okay, my x-intercept is at -5. So basically, to find the x-intercept, you're looking for what makes the numerator of your rational function 0. Next up, we already talked about how to find the vertical asymptotes. So that's the next thing. That's step 4. Step 5 is find your horizontal asymptotes. And when you find these, you want to sketch them, like on your paper. Go ahead and give yourself a little sketch of where these points are and where these lines are. Next, they're going to have you plot several points. In other words, kind of table of values. Pick an x value, plug it in, see what your y value is. That gives you a point on the graph. And they're going to have you do that for several points. And then the final thing is complete the graph. So that is their 7-step process. And they will walk you through that process, but it's all stuff you know how to do. Okay, so let's go ahead and go through that 7-step process. But here's where I have a little bit of a problem with the 7-step process. The first step was figure out whether it has even or odd symmetry. Well, I don't know if I have a problem with it. Let's go ahead and plug in to find out. That's really the only way you can do it at this point, unless you've been doing this long enough that you have a feel for what these look like. Or you could cheat and look at the graph, but you're not supposed to. So let's go ahead and do it algebraically since we have nothing else. If it were me and I were you, I'd want to do this last. I'd want to have some other ideas of what the graph looks like, and then I'd say, yeah, I'm pretty sure it's even or I'm pretty sure it's odd. But there's always algebraically, so let's not skimp on that idea. I don't know why I would originally want to skip that. So this is what it looks like with me plugging in -x in place of x. All right. When I square -x, that's like -1x times -1x. That's going to give me positive x squared. So the top just looks like this. When I square -1x, that's -1x times -1x. That's positive x squared. And look, it looks exactly like the original. So that looks exactly like the original, which is the very definition of what makes an even function. So I know it's going to be symmetrical across the y-axis. There's my first step. Step 2, y-intercepts. I plug in x equals 0 to see where it hits the y-axis. That's 4 times 0 over 0 minus 9. And look, the numerator is 0. Remember, in a fraction, if the numerator is 0, it doesn't matter what the denominator is. That means it's equal to 0. Okay? So if it goes through the x-axis at the point 0, that really means 0, 0 is where it crosses. So when I do my y-intercepts, I better expect to also get this because that's a 0 for y as well. So how do we find the y-intercept again? We look for what makes this equal to, this equal to 0. In other words, it's like 0 equals in that function. Okay? If I'm setting this whole thing equal to 0 and it's a fraction, then really what I'm doing is I'm wondering when the numerator is equal to 0. So what would make 4x squared equal to 0? Well, that would mean x squared would have to be equal to 0, which would mean x would have to be equal to 0. And so again, there's my y-intercept. All right, next, vertical asymptotes. Let's go ahead and factor the top and the bottom here. We weren't asked for the domain, which is a little weird, but we can always talk about that. So this is my numerator and my denominator. That's a difference of 2 squares. So it factors like this. So what makes my denominator 0? When x is 3 and when x is -3. So those are domain restrictions. Every domain restriction, everything that makes the denominator 0, is either a whole if it also creates a 0 in the numerator, which this one does not. I don't have any matching factors. Or it's a vertical asymptote. So I have vertical asymptotes at x equals 3 and at x equals -3. So this is what I got so far. Next, I need my horizontal asymptotes. All right, that's where I look at the degree of the numerator and the denominator. They're the same. When they're the same, that's when I just take the leading coefficients and make an equation with just those two. So y equals 4 over 1. So my horizontal asymptote is y equals 4. All right, what's up next? plotting some points. Okay, so I can pick some points. If I know that this goes through 0, 0, then I know it at some point it's near the origin. I also know it's got some asymptotes at 3 and -3, so I'm probably kind of interested in what happens near there. All right, so I might pick some points like -1 and 1, 2, -2. I'm being kind of haphazard in terms of not going in order, but you don't have to. And then I'm going to plot those points on my graph. Now, let me see if I can go ahead and try to do that on my system here. Okay, so I just checked the math type Blackboard system, and you're not going to have to do any actual graphing. Like, you're going to just choose between multiple choice graphs. So now one problem is they do give you what numbers they want you to fill in. You don't get to pick your X's. Be very, very careful because they do expect you to simplify your answers. And if you you're plugging in like 5 or 6 points, if you get one of them wrong, the whole thing is wrong and they won't tell you which one. So be very deliberate when you're doing that. And then you get to choose based on all this information from multiple choice graphs. And that should be pretty easy at this point because you should have a pretty good idea where it's going to be. You might need to zoom in to see the graph a little bit better, but that's about it. So I hope this has helped you with graphing rational functions, and I will see you next time.